Now we're going to continue talking about instruction set architectures. We're going to go into more detail about what we talked about in the previous lecture and introduce some new issues. So today we're going to start out talking about translation to machine code. And this is converting the assembly that we wrote previously into the ones and zeros the machine actually uses. When we talk about this, the first thing we're going to have to cover is instruction formats. That is, how are those assembly language instructions converted into ones and zeros? And we're going to talk about how you can encode large constants. Then we're going to spend a lot of time talking about procedure calls. Procedure calls are important if you want to be able to access different code that you didn't write. So if you want to call a function that somebody else wrote or a library. And for this, we're going to need to talk about register conventions and stack memory because we're going to need a place to save registers that other procedures are using. Finally, we're going to talk some about other instruction set architectures, other ISAs. And I want to do this to give you a feeling about what other computers are doing. We've seen a lot about what MIPS does, but MIPS isn't the dominant architecture, so we want to spend some time talking about other options. So before we get going, I want to talk about some material that you need to read that's not in this lecture. So sign extension, logical operations, and the assembler, linker, and loader are all from Chapter 2, and I'm not going to talk about any of them during the lectures. You will need 2.4, sign extension, and 2.6, logical operations for this lecture. 2.12 will be on the exam, but you won't need it for the lecture. So please, go read this before doing the lecture. The book has excellent descriptions of this stuff, and will give you another way to learn the material, and just make it easier for you to learn this stuff. So again, you need to have read 2.4 and 2.6 for this lecture. So let's go ahead and get started, translating to machine code, and here we're going to talk about encodings and formats. So instruction format. Machine language is the ones and zeros that computers use. When we write add R8, R7, this isn't something the computer understands. So we have this add instruction here that we know what it means, but for the computer to understand it, we need to convert it into ones and zeros. And here are the ones and zeros for this add instruction in MIPS assembly language. And you can see there are 4 groups of 8 bits here. So this is 4 bytes or 1 word or one 32-bit instruction. Now these ones and zeros aren't arranged randomly. There's a lot of order to it. And you can see those orders by looking at the logical fields in a MIPS instruction. The first part is the opcode, which chooses the operation. Then we have 3 sections for the register files. And then we have a shift amount and a function. So now let's cover those in a little more detail. So when we look at the instruction fields, we see how the instruction is broken up. The first part is the opcode, or the operation code. So this is where we specify if it's an add instruction, or a load instruction, or a multiply instruction. This is 6 bits, which gives us 2 to the 6 possible opcodes. The next field is a register field. This is the first source register, and we have 5 bits for that. Then we have 2 more fields, one for the second source register, and finally for the destination register. And these are also each 5 bits. Now here's a question. Why do we have 5 bits for the register fields? Well, it's similar to what I said about the opcode. So for the opcode, if we have 6 bits, we can specify 2 to the 6th possible opcodes. For the register fields, we have 32 registers, so we need 5 bits to be able to specify each of the registers. In addition to the register fields, we also have a shift amount field. This specifies a shift for some operations, how much we're going to logically shift the data, and a function field. And the function here is sort of a sub-selector. You can think of it, you have an opcode, which is a general type of operation, and the function selects a specific one. So in this case, you can see add has a value of 32 and subtract has a value of 34, and this makes sense. Remember what we talked about in 2's complement earlier on. From 2's complement, subtraction is basically addition, but we just invert one of the inputs and then we set the carry in to be true. So the opcode for subtraction and addition is the same opcode, they just have different functions because they're very similar operations. Now let's talk about constants, or immediate values. So small constants are used all over the code. So here's an example. If A equals B, C equals 1, else C equals 2. You see this all over the place. The question we have is, how can we support this in the processor? We need to be able to get this data into the code so that we can use these numbers. And there are several ways we can do this. We could put the typical constants in memory and load them. And this would be slow, both because memory is slow and large, but also because we'd have to specify the address for every time to load it. When we wanted to get that constant 1, we'd have to go load from memory, store it into a register, and then we could use it. We could also create hardwired registers for them. So this is what we did for 0. Remember, R0 is hardwired to 0. We could create a special register for 1, 2, 3, maybe 8, 16, whatever the special constants were. This is a little tricky because we don't know how many of these constants there are. And if we have a lot of them, we're going to need a lot more bits to choose from all those registers. Remember, we're already using all 32 bits in our instruction field, so if we need more registers, we're going to need a bigger instruction. So what MIPS does is something in between. It allows some instructions to have constants inside them. These are known as immediate instructions because they have immediate values or constants inside them. This way we don't have to store the data in the register file or in the memory. We can store it inside the instruction itself. When we have this, the control logic takes the constant out of the instruction and sends it to the ALU so we can use it just like any other value. So here's an example we've seen before. Here's add immediate R29, R29, 4. So the value 4 here is encoded inside the instruction and is going to be used together with register 29 to add. But there's a problem with this. We only have 32 bits in the instruction, and as we talked about before, we need some of these for the opcodes and the registers. So where are we going to put this constant? And this is a part of the design trade-off in designing an ISA. We need to trade off space for constants and instructions, and how do we do this so we can have both? So what MIPS does is it has different instruction formats for different kinds of instructions. In particular, there are 3 instruction formats. You can see here on the screen the same fields that we saw before for the regular instructions. And the regular instructions that we've seen before are what is known as the R format, or the register format. This has an operation and 3 registers, but no immediate value, no constants. And here's what the R format looks like. It's the same thing we saw before, where we have the operation and then the registers and the shift and function amount. And if we look at this, we can see that we have fields for 3 registers and no field for an immediate. The I instruction is different. This is the instruction which has an immediate. It allows us to have 2 registers and a short immediate. And how does that work? Well, the I format makes a trade-off here. You only get to have 2 register fields in the I format, but you can use the rest of the instruction for your immediate. So this is the trade-off. We only get to specify 2 registers, but we get an immediate built into the instruction. And you can see what happens here. We've replaced the last register and the shift amount and the function amount with an immediate. Now MIPS has one last instruction type which is only used for jumps, and this has 0 registers, but it gives you a long immediate. And so for this format, we replace all of the register files with one long immediate, in this case a target address for the jump. We're going to talk about that in more detail. So these different formats use the instruction bits differently. This is how we trade off the space and the registers. Different formats can do different things and use the space differently. So here's a question. How large an immediate can you have for an add I instruction? Well, if we look down at what we have here on the screen, we can see that the I format has 5 plus 5 plus 6 bits, or 16 bits, for its immediate. In 2's complement, that lets us go from minus 32,000 to plus 32,000. So the constant for doing an addition, or an add I, is 16 bits, so we can have anything between minus 32,000 and plus 32,000. We're going to see later how we can have longer constants. So how do we load these values? Here we are looking at our processor model, and we've got an instruction, which is add immediate. And how does this work? Well, just as before, we load the instruction into the instruction register. The control tells the ALU to do an add, and it tells the register file to take some of the data from the register file. But it also tells the ALU to take some of the data from the register itself, from the instruction register. So here we are, we're loading one of our values from the instruction file, one of our values from the register file, and the other value directly from the register. And this allows us to use the value in the instruction, and that's how we get constants in there. Now, this is a 16-bit immediate, and we have an ALU which is a 32-bit ALU, so what we do is we sign extend it to 32 bits. Finally, we write the result back, and this is how the immediate values are used.